Hi all, Dr. Clark here again. For Fish and Wildlife, today we are going to talk about population ecology number 2. Um, this is just a continuation from the last population ecology lecture. It's going to add a little bit more context to how fish and wildlife management deal with population ecology, or what role does population ecology occur, or what role does it play in managing of populations. So first off, I just want to, we'll just kind of review some of the things that we've went over either in population dynamics, but also in population ecology. And then I'll hit some new stuff as we progress. Now, when we were talking about population ecology last time, I was talking about birth rates and death rates and how you can change birth rates, or you might have a different cohort that has a different birth rate, or might produce different egg amounts, or might have a higher mortality or less mortality. Just depends on the organism. For example, we talked about species of fish that when they're young and healthy and vibrant, they might produce a lot of eggs, and they might be a major contributor to the population. Well, we could say the opposite might be true for something like ungulates or even birds, where while they might be young, they might only produce a few offspring, or maybe they produce offspring, but that offspring is not very healthy because the parent doesn't know how to either protect the young or to care for the young very well. When we're talking about fish, raising of young is fairly rare in game species of fish, so we don't normally deal with that. We will talk about some examples where that may play a role. Okay, but even at that, I want to talk about a different way that you can change birth rates and death rates. And here are two examples. So here is an example of some wild pigs or javelinas. And in certain parts of the United States, these organisms are out of control. They eat massive amounts of vegetation. They will destroy crop fields. They'll destroy people's property, etc. So one management role, or one purpose of fish and wildlife management, is sometimes to knock back or decrease population size. Excuse me. And one way to do that is increase the amount of death rate compared to birth rate. So by having extended hunting seasons or no limit hunting seasons, often those kind of situations, excuse me, are geared towards trying to diminish or decrease populations that might be out of control. On the flip side is adding to the population. So here you can see a game and fish officer who's throwing in fish, stocking fish into this river system. That is a way to increase the population without natural birth. However, in some situations, if you're stocking fish that you expect to return and have some kind of reproductive rate, it could be, in a lack of better terms, you could be killing two birds with one stone. In other words, you could be increasing the population by introducing new individuals to the population, stock to the population, but in return, that some of that stock might reproduce also, and so you might get some natural reproduction out of your stocked individuals. Okay? These are ways at which you can change birth rates from kind of the natural ecosystem. We'll talk a lot more ways as we progress throughout the semester, and you'll get an idea of what's going on. Okay, so let's jump into kind of describing population growth mathematically, this is going to be a little bit of a review, mainly because we did this when we were talking population dynamics, but I want to make sure that you guys understand the mathematical equations and how in the future we're going to manipulate certain things, and you'll have to be able to memorize these equations, or at least have them written down to where you can go back and manipulate them very easily. So remember that N represents the population size, or the total number of individuals of a single species in an area at the same time. R is the rate of increase, or the rate of growth that the population has. And we'll talk about different types of R's, and we already have. Okay, intrinsic rate of growth means that there's no limit to it, and then a actually calculated rate of growth means that you're taking into account the birth rate, the death rate, the number of migrants coming in or leaving the population. Time, okay, and again, like I said before, time is based on the species. Sometimes it's represented in year, like a year is the time measurement, months, possibly days, even multiple years, maybe a 5-year period, a 10-year period, etc. So we know that the geometric rate of increase, so this is the best case scenario, okay, would be represented by this equation. So the population over some time period, okay, is equal to the current population at time 0 times the rate of growth for that time period. Okay? So pretty simple. That's considered exponential growth, or geometric growth rate. And like I said before, it has no limit. However, if you remember back to my population dynamic lecture, I said that all populations will eventually have a limit. They will eventually reach their carrying capacity. Okay? So that kind of brings us to when resources are scarce or slow, that exponential growth will slow and it will reach carrying capacity. Okay? Now, carrying capacity could be based on lots of different resources. We talked about this before. It could be food, it could be water, it could be habitat, nesting sites, it could be the amount of predators, it could be diseases. There's lots of things that can set that carrying capacity. But again, once carrying capacity is approached or you're getting close to it, your growth rate or your growth curve is going to move from a J curve, which is the exponential growth curve, into an S shape or sigmoidal growth curve, which is your logistic growth curve. Okay, so logistic growth again is represented by some time interval, some population interval, okay, and we know that now in our mathematical equation we have introduced K. So this equation is a little bit different. It's the same equation as before. It's just represented as a little differently. Okay, so where you have R, this is calculated R typically, so birth minus death plus immigration minus immigration times your original population at whatever time times 0 that is. Okay, 1 minus n divided by k. Okay, so again, as n approaches k, this number gets really small and this number gets really small, which in return changes your population size, or your growth of the population. Well, it doesn't decrease, but the rate of growth decreases. Okay, you can have decreased rate of growth if your R becomes negative. So if you have a negative R, your population could actually be shrinking versus increasing in size. And that does happen. It happens often when populations overshoot their carrying capacity, or when humans get involved and we increase the death rate over the birth rate, or we take too many individuals out of the population and there's not enough to replenish the population. Okay, so that's kind of just an overview of population dynamics. That's, those are the equations that I've given you before. Now let's talk about some factors that can affect the population's growth. Some of this is review and others will be new to you, okay? So when we're talking about logistic growth populations, or populations that have a carrying capacity, which is all populations eventually, but ones that have a carrying capacity are often what we call density dependent. Okay? That means that as the density of the population changes, typically as it increases, the rate of growth will typically decrease. Okay, so as you pack more individuals into a given region, the rate of growth will decrease. Okay? And this is often the case when we're talking about places that have limited food resources, or limited habitat resources, limited water resources. Okay, you can reach these density dependent factors very quickly. Okay, so some of the ways at which this can affect a population can be through disease. All right, there's a lot of books out there currently about human populations, and human populations are edging towards our carrying capacity. At least what ecologists believe the carrying capacity of humans on the planet is, okay? So if you believe some ecologists, they say it's 9 billion. We're at about 7.8 billion people right now, so we're approaching our carrying capacity if it is 9 billion. Other biologists, ecologists, believe it's closer to 12 billion. That's the carrying capacity. Either way, we're approaching it. We're getting up there as a population of individuals on this planet. So why I'm bringing this up is there's a lot of books out there that are interested in, well, what happens when humans reach the carrying capacity? Because we are the smartest species on the planet, or we have the capabilities, the highest capabilities of intelligence on the planet. Not necessarily always the smartest, but we have that capability. What happens when we reach our carrying capacity? A lot of books have been written about this disease. And we know that things like, the flu epidemic, the Black Plague, we know that times in human history when we've experienced massive death due to disease, it always hits the density or the most dense regions the hardest. And that should make sense to most people, is that the more tightly packed individuals are in a given region, the easier it is for diseases to move through those individuals. You can also see physiological stress. Okay? The more competition there is for resources, the more stress there is on an organism, whether that be human. I mean, go to Walmart on Black Friday, okay, and tell me that you have no stress. Okay, I mean, unless you are extremely good at stress management, Black Friday at Walmart, or really any department store, can really cause some physiological stress to individuals, increased heart rate. And there's a lot of actually evidence of this. There's been many people that have been hooked up to monitors and then go to events like Black Friday, or large social events, rallies, these kind of things, and just experience the high density of individuals in one given region. And you can see the physiological stress on those individuals. The other thing that it can do, not from a human point of view, but from other organism point of view, is it can really increase predation rates. Okay? The more tightly packed individuals are, the easier for predators to get a prey item. So So the other thing that can occur is you start to see these density dependent factors like disease, parasite load, physiological stress, predation, starvation, these kind of things. As the population increases, they intensify. So yes, you might have disease that occurs in low density populations. Of course, you are going to have disease. But as you increase the density of that population, you're going to increase the rate of disease. Okay? So, other things that can occur are density independent factors. We talked about this just a little bit before, and that's things that really, whether you have a drought or a fire or a hurricane or a tornado, whether that strikes a specific region is rarely due to the density of organisms in that given region. Now, there has been some evidence that suggests that, droughts, fire, tornadoes, and some of these other things are more intense in regions where there's high populations. And that's because at least high populations of humans, and that's because we alter the ecosystem. And so we get changes in the environment around those ecosystems. So, for example, if you ever look at a thermal map of the United States, you can see where all the major cities in the United States are. And that's because these are thermal environments that are much more warm than the surrounding environments. And that's due to asphalt and concrete and all these other features that we have that absorb heat and hold heat, much better than, say, grass or trees or even just bare soil. And so you can get these heat pockets around these cities, and that can change the weather system, okay, in a given region. Right? And there's pretty good evidence that suggests increases in tornadoes and things like that can be due to the more concrete and more asphalt you have in a given region can intensify the not just the amount of tornadoes you have, but the severity of tornadoes. Okay, so density independent factors, however, often are not selecting for how many individuals are in a given region. Okay, whether or not a fire breaks out or something like that, the direction that the fire travels has nothing to do with the density of the individuals. Now, whether the fire occurs or not can have a density dependent effect. I mean, obviously, the more individuals from a human standpoint you have, the more individuals you have in a given region, the higher the likelihood that one of those individuals is going to start a fire. This is true, okay? But humans aside, when we talk about density dependent and density independent factors, most of the time, drought, fire, weather is density independent. Density dependent is things like disease, predation, parasitism, starvation, those kind of things. Okay, so that brings me to talk about R-selected and K-selected species. Now, when we're talking about these different kind of ways to group species, I want you to think about specific examples of organisms that you would say, oh, that's an R-selected species. Okay, so an R-selected species typically has a very high mortality rate as offspring. So it produces lots of offspring, high reproductive rate, lots of offspring, but not very many of the offspring actually survive. They're also normally categorized by having very little parental care. So it's basically just shoot out all your babies and leave, and the ones that live, great, they're the ones that will carry the genetics on, and the ones that don't, they're food for something else. Right? So that's an R-selected species. K-selected species typically have very low reproductive rates, so much lower reproductive rates. They have a slower growth rate, and they normally exercise pretty heavy parental care, I guess you could say, or a lot of parental care, or at least it's a lot of parental care for a small period of time. K-selected species are typically close to the carrying capacity. So because they have very low reproductive rates, a few individuals here and there is not going to make you bounce over the carrying capacity. R-selected species, on the other hand, they often are situated with what we call boom-bust populations. So you might have good food resources, good water resources, etc. at a given time. That population might explode and overshoot its carrying capacity, overconsume the food resources, and then crash. Okay? K-selected species rarely do that. It normally takes them a very long time before they reach carrying capacity. They sit at carrying capacity for a long period of time, and they occasionally bounce over it or, under it. But you don't have these big busts that you often see in R-selected species. Okay, so a couple other things about R-selected species. Typically, they're shorter in lifespan. They have earlier maturity. They often are better at adapting to unstable environments. Mainly, they're lower on the trophic level, meaning they're food for a lot of other things, normally K-selected species. K-selected species, pretty much the opposite of R-selected species. Longer lifespans, later maturity. They adapt well to stable environments, but have a hard time when the environment changes. And they're normally the individual that's consuming R-selected species. Okay, so remember when we said growth rate is the product of birth rate plus immigration. You can write it this way too. So birth rate plus immigration minus death rate plus immigration. Okay. So you have the number of individuals coming into the population, either from birth or migration, minus the number of individuals leaving the population, either through death or immigration out. So births, the number of births that occur in a population at any given time, we've already talked about that. Immigration, number of individuals moving into the population, we already talked about this. Death, the mortality, okay, the number of individuals leaving via death in a given amount of time, and immigration, or leaving the population, moving to another population. Okay. We've already kind of hit on this pretty hard. I just wanted to really show you that you can write these equations in different forms. When I originally wrote it for you, I wrote it R is equal to B minus D plus I minus E. Okay, but you can write it as B plus I minus D plus E. Okay, so just be prepared that equations might not always be identical to the way that you originally saw it. So you might have to use some algebra to convert that equation to something that you remember, or you can just use the equation as it stands. If I give you an equation, you know that the equation is legitimate, and that's an equation that you can use to calculate whatever it might be, in this case, growth rate. Okay, we talked about this a little bit. Lifespans, this is the amount of time or how long a given individual will last. And it depends on Well, first of all, it depends on if you're R-selected species or a K-selected species. But even within K-selected species or R-selected species, there's a huge range of life expectancies, and they will also be determined by the ecology or the environment that that organism lives in. So you might have a life expectancy of a certain species of rabbit, might be 4 or 5 years in one population, but in a ecosystem that might have lower predation rates, it might have lower disease rates and higher food resources, you might see that the life span for that organism is maybe 8, 9 years in that other ecosystem. Okay, so normally what we will report for a given organism, or what we're interested in a given organism, is their maximum lifespan. Okay, so this is the oldest that any individual within that species has ever lived. Okay, so the oldest organism on the planet is bristlecone pines, okay, and they live up to 4,600 years. Maybe even longer than that. We don't know, because they're hard to age. I'll talk about aging trees a little bit later on, mainly because you can age fish and indeterminate growers, um, species that grow forever, basically continuously grow throughout their lifetime. They grow, or they have a pattern of growth very similar to trees. And I'll talk more about this as we progress and we start looking at how to age organisms. But nonetheless, bristlecone pines, they're hard to age, and it's not worth cutting the tree down to get an age, because you ended the organism's life. So there's other methods that we can do this, and I highly suggest watching this YouTube video on bristlecone pines. They're kind of a neat organism, neat tree, and it gives you some information about some researchers that may or may not have made some major mistakes when trying to age bristlecone pines. And I'll let you watch that if you so choose. So humans, I'm not entirely sure what the oldest individual to ever live was, like how old they were, but it's somewhere around 120 years. I give or take a couple years. I'm not entirely sure. Okay. And then if we're talking about things like, a lot of the diseases or the microbes that might be affecting fish and wildlife, and they might only be alive for a couple hours, but given their population sizes, it really doesn't matter if that bacteria dies, because a new one has already been reproduced tenfold, hundredfold, 1,000-fold over. So some microbes can only live for a few hours. Okay, so the differences in longevity, or kind of the lifespan, or I guess you could say, the allocation of energy to a lifespan, can be represented in what we call survivorship curves. There are 3 general survivorship curves. They're called different things, but normally you have a type 1 survivorship curve or type A survivorship curve, and that means the organism has a very long life. It survives very well from childhood all the way to adulthood. Now, once it reaches close to that maximum lifespan, then you have a huge drop off. Almost no organisms make it past a maximum lifespan, but they have low birth rates typically, and they just last for a long time. So elephants, bears, humans, etc. Pretty much, if the organism survives through childhood, it pretty much has the exact same survivorship throughout the rest of its life until it reaches its maximum lifespan, and then it starts tanking really fast. Okay, type 2 or type B survivorship curve is the probability of death is really unrelated to age. It's basically a constant death rate. And most birds fit this pattern. A lot of other small mammals will fit this pattern. And that means basically if your death rate at birth is 10%, then your death rate when you're 2 years old is about 10%. And when you're 5 years old, it's about 10%. And the death rate is really unrelated to age. It's just a constant death rate. So you normally get kind of a straight line, or your curve is pretty straight. Okay, and then type 3, or what's sometimes called type C survivorship curve, would be mortality is extremely high, young in life, and then you have a fairly consistent death rate throughout the rest of your life until you reach your maximum lifespan. So high mortality, and then it's pretty constant. And I'll show you it on this curve here. So here you can see, type 1 or type A, you have this fairly constant survivorship until you reach close to that maximum, and then you just tank as a population. So, I think the human population, our life expectancy is somewhere around 80 years old, 78, 80, it depends on the sex of the individual. Okay. After that, it's, your death rate is increasing, at least as a population. After basically 80, boom, it starts to tank. But up to that point, it's pretty good. It's pretty constant. Okay, B, so most birds, etc. Okay, it's just a straight line down. Okay, C or type 3. Okay, this is like a lot of fish, a lot of insects, a lot of plants produce massive amounts of young. A lot of them die. The ones that survive at a constant rate until they reach their maximum lifespan. Okay, so that brings me to a little bit more about populations and how populations interact with each other, okay, or between populations or within a population. So that there are two terms for this: intrinsic factors. Okay, intrinsic factors are between individuals of the same species, normally between individuals in the same population. So this might be competition for food resources, competition for mates, okay, competition for habitat, etc. Those are intrinsic factors that happen, within a population between the same species. Okay. Extrinsic factors, okay, are from outside that population. Okay. Sometimes it can be the same species. Other times it can be intraspecific factors or another species that is affecting them from outside. It could be a predator or something like that. Biotic factors are factors that occur from living organisms. So biotic meaning living. So most of the time, like I said before, these are density dependent. Abiotic factors, A in biology means non, so abiotic meaning non-living. Okay, these tend to be density independent. Okay, we talked about this before. Again, these are weather related, typically, whether that be, temperature, humidity, precipitation, wind, whatever it might be, those are abiotic factors. All right, so density dependent factors. There's a couple situations that I want to talk about when we talk about density dependent factors and the role that managers might play in such events. Okay. If we have huge populations that we see that maybe disease is fluent in the population, okay, or running rampant in the population. Maybe they're destroying lots of crops. Maybe there's a lot of malnourished individuals, um, these kind of things. Then density is out of control, typically from a manager's point of view. So ways at which we can manage that from a density dependent factor is to try to reduce the population size by either decreasing the number of individuals that are born. Sometimes we do this by trying to do sterilization events, those kind of things, or by increasing mortality. Okay, so those are really the two ways that we can do this. Change the birth rate or increase the death rate. Okay? And here's an example of increasing death rates. So here you can see a couple hunters and a whole pile of snow geese. Okay, and a couple years back, well, I shouldn't say a couple, maybe 10 years, maybe more than that, maybe 20 years ago, there was a huge population explosion of snow geese, and snow geese had basically became right at their carrying capacity and doing massive amounts of damage to croplands, etc. And so Game and Fish at many different states came together and they decided, hey, we're going to have snow goose hunting seasons. In the fall, you rarely see snow geese because they're on their wintering grounds already, and you really don't see them very often. But in the spring, you can see huge amounts of snow geese. And so they would often, most states, and they still do this in a lot of states, they offer spring hunts on snow geese. Okay? And often it's regulations are changed. So they often have no limit on the snow geese. They did again. It depends on the state, but a lot of states mimic the same regulations. Okay, so no limit. You can shoot as many snow geese as you want. You can use more than 3 shells in your shotgun. Okay, so you can remove the plug in your shotgun and use 6 shells. A lot of states allow you to electronic call. Okay, and just other regulations that normally don't you can't do during a typical hunting season. And those are management programs from the point of view that the population has been deemed overpopulated or too many individuals, and the management is to reduce the population. Okay, so there's other situations where this is kind of a natural situation, where you get predator to prey oscillations. And we talked about this before when we were talking about the lynx hare cycle, etc. And you get this predator prey oscillation. And it happens interspecifically between two species. So you don't have, this situation where humans have to step in. You know that the predators are going to rebound and take out the prey numbers because the prey has exploded. That's what we were actually hoping with snow geese. As the population increased, we were hoping that the predators might increase and take out a lot of the young snow geese and things like that, but it didn't occur. So managers felt like they should step in and reduce the population via hunting seasons. It makes a lot of hunters happy. Does it work? We'll come back to some of these management decisions and we'll look at how long they've been running and whether or not they work. Okay, but nonetheless, that is a result of a density dependent factor. Other density-dependent factors, okay, is intraspecific competition between individuals. Here's a great example of that. There are populations of deer, white-tailed deer, and mule deer in certain regions that the populations are so high that you have huge events of starvation during wintertime. Because there's that competition for food resources. These populations just get out of control. You can have very large amount of deer dying over winter due to starvation, disease, etc. And part of that has, and it's density dependent, but part of that is the intraspecific interaction between individuals. They're competing with each other for food resources typically. So again, like we talked about before, as that population density is approaching carrying capacity, a lot of what's making that carrying capacity set is, certain resources. It could be more than one resources. It could be food and water. It could be food and shelter, water and shelter, whatever it might be. But as the population is reaching carrying capacity, you know that those resources are becoming limited. Okay? And you can start to see some changes in the population. Starvation, hypothermia because there's no shelter. Lots of things that can occur. Okay. Again, depending on the species, you might see increases in, territories or territorial defense. And so you might see as resources become more limited, species spend more time defending their resources against rivals. This happens a lot in birds. So birds, as the density increases, they'll defend their nest sites, and to the point where if the density is high enough, males will defend the nest site and won't reproduce. So they'll sit there and defend night and day, every second of the day, and they won't reproduce because they don't have any time to reproduce because they're defending their territories against rivals that want to encroach in on their territory. And that has to do with that intraspecific interaction between individuals of the same species within the same population. Okay, this can also increase stress-related diseases. Okay, again, if heart rates are up, if tension's up, okay, if the amount of energy is needed to fight off diseases is not there, that can cause individuals to become sick. Now you're right next to another individual, which can cause them to be sick, etc., etc., etc. And you get this stress-related diseases that often happen as populations reach those carrying capacities. Okay. All right. So that's kind of the last little bit of what I want to talk about with population ecology. We're going to move into talking about the history of game and fish real quick, just because I want to, after midterms, I want to concentrate mainly on techniques that occur in fish and wildlife management, techniques for many different things, techniques for aging populations, calculating population sizes, mark recaptures. So how do you capture them? How do you mark them? How do you sex individuals? These kind of things. So after midterms, that's going to be the concentration. Is we're going to really dive into some of those techniques. You're going to see a lot more videos of hand-on techniques, me demonstrating how different techniques are carried out and whatnot. Okay, so next time, the history of game and fish.